So lesson 88 is on exponential functions, which you did some of last year, and it was growth and decay. And so a couple of things that we want to remember about these. Growth is when it is increasing. And decay is when it is decreasing. And you hope that money that you invest is growing exponentially, compound interest, radioactive decay, the amount of carbon is declining over time, or, well, when we do the carbon dating, that's when the amount of carbon is decaying exponentially. But any radioactive substance, we talk about half-lives and the amount of radiation that's active in something decreasing over time. What is important that we remember and memorize is our formula for that. And it is going to be the amount at time t equals, so AT is the amount after some time t. 10 seconds, 10 days, whatever the units might be in there. A0 is the amount at time 0. It's the starting amount. So the initial amount, the starting amount, the amount at time 0. E to the KT, K is the growth or decay constant for that problem. And we're going to need to be finding K for each problem with the help of our calculator and storing it. If K is positive, it's going to be growth. And if K is negative, it's going to be decay. So a couple of things here on our graph. This is going to be time. The y-axis is going to be our amount at some given time. It's a function of time. If t is 0, when we have a starting amount, that means our y-intercept is a0. So if it is growth, it is doing like this. And k is something that is bigger than 0. If it is decay, this is still our amount at time 0. This is still our time. The y-intercept is still whatever the amount at time 0 is, and we could actually write a number in there. This is decay, and k is less than 0. So everybody okay with that? What it means, if it is exponential, it is growing or declining faster than linear. Because at some point, now I might initially have a line that's up above this, but if I do a straight line, say like that, eventually the exponential function goes up above that and is shooting up a whole lot faster. Or the same thing for decay. So I basically already did all of that. So let's do some examples. The number of bacteria present at noon was 400. 9 hours later, 800. Assume exponential growth. So it is going to fit our model. So we always want to start out writing down the formula in general, and then we'll show our substitutions. So you need to write down the amount at time t is always the starting amount, e to the kt. We're predicting k is going to be something positive since they tell us that it is exponential growth. But we're going to now plug in what we know from the first sentence there. The amount present at noon was 400. That is our starting time for this problem. So we can put a 400 in for the A0. Okay, 9 hours later, So that means t needs to be 9. And so then we're talking about a 9 for this problem, which would be 800. And the t has to be 9, so we have the k times the 9, or 9k. E is a number, and we have now an exponential equation that we need to solve. So what do we do when we have an exponential equation in now? We need to get it where it is e to something, and then we can take logs of both sides. So first step, show that we're dividing both sides by 400, which means I just have 2, which equals e to the 9k. How do I get rid of the e, Anna?
You can multiply both sides by ln.
It's not multiplying by ln. ln is not a number, it's an operation. So we need to take the natural log of both sides. Right idea, I just want to, then that's a hard thing to get used to. But what we need to do is to take the natural log of both sides. So now I have 9k is the natural log of 2. Must always write down exactly how are you going to enter this on the calculator. You are now going to enter k equals natural log of 2 all over 9. It is not the natural log of 2 over 9. Be sure you go outside of the parentheses for the natural log when you do that. And then I want you to store that as k. And I want you to write down the rounded value for what you get, just for my reference sake, for checking. So let me do that on my calculator here with you. Okay, so on a calculator page, we were entering, let me get my fraction bar in there, and then I need natural log 2, get down in the denominator and divide it by 9. Is that what you guys got? Mm-hmm. And then we are going to store that as k. Where's my k? And then we are going to write down that it was approximately 0.077. But then we will be using the stored value in our problem. Okay, now we have stored it. Now we need to continue with the problem. So let's see, it wants us to write the general equation. So don't put any other numbers in yet. So we are now going to say that our general equation is the amount at time t is the starting amount is 400 no matter what time we want to talk about, e to the, and then right here we are going to enter this because it asked for a general equation that if all we gave to somebody else was this, they'd know how to type it in their calculator. And then they are going to, then you're going to say the natural log of 2 over 9 times k. But now we want a of, let me do that, will it? We want the amount present at noon the next day.
Wait, Ms. Smith?
Uh-huh.
Shouldn't the k be t?
You're right, thank you. I need you guys to keep me honest here. That was k, and then we need to be multiplying that times t. That is our general equation. Now, what we are going to do, we want the amount at noon the next day. How much time has gone by from our starting time when we get to noon the next day? So 24 hours have gone by. So 24 hours later, that needs to be our new t. So we're going to label, we're finding the amount at time 24. That needs to be 400. Now, when we're going to type in our calculator, we're not going to type in ln2 over 9 again because we stored it. We're going to type in 400e, and I put the box around k to remind me it's something that's been stored, times the 24, or times 24k. So we go back to our calculators, and we now type in 400. Same thing again there. So 400, and then when we want e to the something, get my 400 to show up, e to the x button, and then we can do either k times 24, or I'm just going to do 24, and then my stored k, and then enter. And I always want to see rounded to 3 places, and then maybe also rounded to an integer depending on the context of the problem. So we're going to copy that down, so it'll be a 0.842 as we copy that down in there. So let's see, 2539.842. Going back to your paper, write down 2539.842 bacteria. And if you think that it makes more sense in the context of the problem to also write about 2,540 bacteria, you may do that, depending on the context of the problem, because you wouldn't really have a fraction of a bacteria in there. But I want to see the decimal just to check your work that you were on the right track. Everybody okay there? Okay, let's do a couple more of these because I know it does take some getting used to. So we always begin with our general equation, the amount of time t, the starting amount A0, times e to the kt. Plug in what we know when the experiment began, so our initial amount is 1,200. After 100 hours, so when the time is 100, the amount at time 100 is 2,700. First thing we need to do is to figure out what k is for this problem. So we need to isolate e to the kt, divide both sides by 1,200. And let's see, 27 over 12, those are both divisible by 3, so 9/4. Or if you're a decimal person, 2.25, if I did that right. So far, so good? Equals e to the 100k. So what do we need to do to both sides? We need to take the natural log of both sides. And then we have 100k equals that. So we need to enter on our calculators. K is, I think I'm going to go with a 2.25 since that's exact. I couldn't do it if I had to round it. But that's not quite as messy to enter on my calculator. And I am going to store this as a new value of k. And I'm going to write down approximately what it is to help me know when I'm grading your work. Did you just enter that wrong on the calculator and then that's what threw everything else off? Or was there some other problem that I need to help you understand what you did wrong on it? So natural log of 2.25 divided by 100. Down this time. So control divided by control natural log 2.25 divided by 100. Is that what you guys are getting? 0.008109 and so on. And back to my paper here. So K is, oops, I didn't write it down on mine. What did we have again? 0. What was it? So 008. And if you wanted to really help me out with what you got, what were the three significant digits? What were the next two after 8? 1, 1, 1. So I take it either way, but better if you can get three significant digits in there. Did everybody store it as K? Okay, I don't think I have on mine yet. I'll have to remember to do that in a moment. Okay, now we want to know, so we're going to always write our general equation then. So our amount at time t is 1200 e to this natural log 2.25 over 100 times t. I think I got it right that time. What we need for this problem is we want to know how much time until we have 30,000. So we don't know what t is going to be this time around. But we want to put in 30,000 for this amount, and that's going to be 1200 e to our stored k times t. So divide by the 1200, and we have e to our stored kt is, what is 30,000 over 1200 reduced to? What? 25? Then what do we do, Britt? So that's going to be k times t. We want t. Our calculator knows k. So t on our calculators will now be the natural log of 25 divided by, with our box around it to say it's our stored k. And Dylan, what did you get when you put that in? Can we have fractions of ours? Yeah, so we'll just leave that as our decimal in there. Anybody with a question on that? It still says to draw a sketch, but so far, any questions? Thumbs up or down at home? Okay, then if we want to draw the sketch, we have exponential growth. So we're going to be doing something like this. This is our time. This is our amount at time t. My y-intercept is how much on this one? Shout it out in class. What was my starting value? 1,200, 1,200. So that is my y-intercept. So I have to label that. Then, let's see, what did I have on there? Okay, I could label another point if I wanted to, but I'm not really going to worry about scale on it. The other point that I know is after 100 hours, there were 2,700 bacteria. So I could just kind of, well, see, a little more than double that. So about twice as high on that. That point would have to be 100, 2,700. It would have to be somewhere on there. Does that make sense? And let's see. 2 more maybe? I think we're doing okay on time here. Okay, amount of substance initially present was 400 grams. So in general, amount at time t is A0 e to the kt. Initially was 400. Okay, after 90 hours, so time is 90. The amount at time 90 is 380. It's getting smaller, so this one has to be decay. And that was 90 hours, so 90 times k. What do we need to solve for first? K. So divide both sides by 400. And we have 38 over 40, or 19 over 20. Could do that as a decimal if I wanted to. Is e to the 90k. Now what do we do? Natural log of both sides. That will be equal to 90k. So k needs to be the natural log of 19 over 20 divided by 90. So a little bit messy to enter with a fraction. Again, you could change it to a decimal if you wanted to, but I want to model at least one where we are needing to enter a fraction in there. So, where'd my calculator go? So now I am entering control divided, so I've got my fraction bar, and then I'm doing the natural log of, and inside of that fraction bar, 19 divided by 20. Whoops. $19 divided by 20, and underneath divided by 90. And are you guys getting a negative like we would expect for exponential decay? And did you also get the negative 5.699? And then we store that as k once more. And we write down negative 5.699. And now we've stored it. Our general formula is the amount at time t is starting amount 400, e to the natural log of 19/20 all over 90 times t. We want to know the half-life. Parker? Was it? Well, thank you. You're exactly right. It was times 10 to the negative 4. My bad there. Thanks for that catch. Trying to rush to get to this test. So times 10 to the negative 4. So it really is a tiny k in that. Okay, now what does half-life mean? We're supposed to try to figure out the half-life. What are we talking about with a half-life? Anybody know from science classes? What does it mean for a half-life? Parker?
It's like the time that it happens
Okay, the time it takes for half of it to go away, whatever the it is. So if it's a debt, the half-life would be how much time does it take for me to cut my debt in half? All kinds of things with how many atoms, if we're talking typical applications in science. So, two ways you could set this up. You could say, oh, if I start with 400, the half-life is talking about when do I get to 200. So you could put a 200 in here, so I want to know the time when the amount is now 200 instead of 400. And solve it from there. Or, if you solved it from there, what would be the next thing you do? You divide by 400, right? Which would mean you would have a half is just e to the kt. Now, if I had started off with 3,264,911.43871, do you really want to take time to take half of that? You could, or this is your half-life formula. You don't need to memorize it, just that the amount is now a half of what you started out with. So if you think of starting out with 100% and then having 50%, or 1 and then having a half is 1 e to the kt, if you're just getting the half-life. So then we need to get t, so we're going to take the natural log of both sides, and then we are going to divide both sides of that by k. So to get t, we're going to take the natural log of a half and divide that by our k. Emma, you have it already? What you got? Excellent. So the half-life is, and so the time to have half of what we started with, we'll label that T1/2, is 1,216.207, and it is hours. And then we need a sketch. So this time it is decay, so we need to draw that it is going down like this. Our starting amount was 400, so that's our y-intercept. This is the y-axis is our amount at time t, the x-axis is our time. And then half-life, this is not necessarily going to be the scale. Half-life would be okay, let's draw a dot about halfway between 0 and the y-intercept. Come straight across, come straight down, and this needs to be 1216.207 hours. So is that kind of making sense of the graph? And my curve is probably should have been steeper or not as steep. I'm not worried about that. I'm just, are we understanding the relationship in that? And then final example for the for today. Okay, radioactive decay. It's decaying exponentially, and we know 2 points in time. And we want to know the amount that was initially present. Now, there are a couple of ways that we can set this up. And let me think which way I would rather do it. Okay, I can either do my amount, well, I'll do my general equation first. I can say that after 100 years, I have 500 grams after 100 years. And I don't know K and I don't know the initial amount. And then I can do after 200 years, the amount is 300. And then I've got a system that I need to work through and solve. And I can do that, and I can model some things for what that would look like if we want to do that. The other way that we could do it, and then we need to find amount at time 0, and we'll figure out what our K is, and then we'll figure out the half-life. The other way we can set this up and do it is we can let time 0 be 100 years. That means after 200 years, how many years have gone by since my starting time of 100? So then I could say, so 100 years is time 0. I could say after 200 years, that's going to be T100. And then I could say my initial time is 100 years before I started off in this problem. So I can say my initial time is going to be negative 100 when I'm trying to find that to answer the question. Math will be easier this way, but the setup is a little more confusing to keep track of. So there's a trade-off. So let's do it this harder, more confusing way with the setup first. So if I wanted to set it up this way, I would need to say, so 100 years is now my starting time, and I have 500 grams. And then I can plug in 100 years later and have 300 grams, so after 100 years have gone by. Then I can say 3/5 is e to the 100k. So take the natural log of both sides, divide by 100, and that needs to be my k. everybody doing that? Okay, then I want the amount initially present. So that means 100 years before I started this setup. So that's going to be the amount 100 years before I started the setup in this one. Now needs to be, my starting amount for this one was 500. E to the negative 100, plugging in for my time, times your stored value. You guys all getting that punched on your calculators so that you can help me out with what we come up with here? And I don't have it worked out this way on my paper, so I'm changing my mind on how to teach you as I go along. People at home, are you getting it punched in? And Anna, what did you get?
I got 833.23.
Thumbs up, everybody agreeing with that? At home, everybody agreeing with that? Any questions on that setup and how I got those numbers in there? Any point on the timeline can be your starting time. You can start at noon, you can start at 2 p.m., you can start 100 years in the future, wherever you want your starting time. But then you just have to make sure everything else in the problem is relative to that. Like when we started at noon one day, and then we wanted noon the next day, oh, that was 24 hours later to figure out what to put in there. Okay, if I did it this other way, if this way in green makes more sense to you for how to set it up, we haven't ever solved a problem that looks quite like that. I can take, and instead of adding the rows or subtracting the rows, I can divide the rows. Except I'd rather have my 200K on top and my 100K on the bottom. So I'm going to switch my system around and say, oh, I had 300 equaled A0 e to the 200K, and I had 500 equals A to the 0 time, or A0 times e to the 100K. Oh, my A0s cancel out and I have a 1. And on this side, I have a 3/5 or a 0.6. Oh, I have e to 1 power over e to another power, but the same base. So I need to subtract my exponents. And if I take 200K minus 100K, my new exponent is 100K. Then I can take the natural log of both sides. So I have 100K equals that. Divide both sides by 100. And now I'm going to store that K is the natural log of 0.6 over 100. Hey, I got the same K. Is that making sense to everybody? Okay, then this way, once we had that, then what did we need to know? Okay, then if we did that, we need to know, so now we know K, and we need A0. So we can plug into either one of these. So I'll plug into the 300, or I'll do the 500. I like 100 better in there for my exponent than 300. So now I can take that, and I can go back to one of my starting equations, because I've now found one variable, so I plug it in there. I want to get A sub 0. So I need to, this is going to be a little bit messy here, I need to, what did I have there? Okay, so I'm going to have all of this. Now, it might be a little bit easier on this one. I could just punch it all in like that. I could do 500 divided by all of that I've stored, and that's fine. you could do 500 divided by e to the 100 stored k to get your starting amount. Do it that way if you'd like. Hopefully we'll get the same thing. The other way you could do it is you could say, wait a minute, I know that k is natural log 0.6 over 100, so my hundreds are going to cancel. And I know e to the ln cancels, so that's just 0.06. So all I really need to do is to divide the 500 by the 0.6, and I will have my initial amount. So a bunch of different ways we could get there, but we'd get 833.33333 grams either way. Make sense to everybody? Okay, now let's look at what we've got for our equations. And then we'd want, if we're going to use this as, well, actually we don't need to do that. To get our half-life, remember we're going to say, oh, we need to get a half equals e to the kt, half equals 1 e to the kt. So either way now, for our half-life, 1/2 equals e to the kt. So natural log of both sides. Divide both sides by our stored k. And Dylan, what's our half-life? And those would be years. Anybody with questions on these exponential problems? Again, I've tried to model that there will be several ways that you might approach these that are equally correct. So think through what's going to be the easiest for you on a problem, what's going to be the easiest one for you to keep straight and follow through with.